Thank you for being here on a Friday, 4 o'clock, after 2 days of CEO, functional programming, CEO, and then again CEO, without a coffee break and without almost break. So thank you for coming, really appreciate it. And yeah, it's going to be a fast talk. We only have 25 minutes, but we'll try to keep the pace for all the content we have. Dotty is the next version of the Scala language, and I'm really excited that it's going to have union types. It's a feature that it's a disjunction on the type level. It's basically the eithers at the type level. But apparently I'm the only one that hasn't made much noise. And we'll see also what are the issues with the encoding of the union types in Dotty. So after we solve those issues, I'm going to present a small micro library. Well, it's not a micro library, some POC I'm doing trying to overcome those issues and tying it to logic. So we are not going to do the usual basically logic at the type level, but we'll work about function application in Dotty that ties it to a more logical way of programming, in my view. So let's start with, this is Dotty. I'm using the worksheets, so all the code is live, and we are going to compile it and evaluate it. So union types, you see, for those of you that haven't seen it, we see string or boolean on the line number 7, and here I'm proving that string or boolean is the same as boolean or string. That's something that, for example, in Scala 2 we cannot do it. We have like simplification, like a string or strings equals strings, and one quite important, a string or nothing equals string. So if you keep this in mind, these are going to become handy throughout the talk. So this is one of the examples of, in Dotty, you have type level reasoning. You can use that. And we see almost compiled. So basically all the green lines says a generalized constraint, which is the way of the compiler telling us it found a proof for that statement. So basically we have this proposition and it's been proven. Unfortunately, the last line, it's in red because, yeah, I was expecting that something and any will be any, but the compiler doesn't agree with me. But there might be some reasons behind it, but again, logic. What's the advantage of this union type? For example, we could unify a lot of the encodings we have for optional types, like either when there is some disjunction, it's either A or B, or validated if you have a good result of an error, or obviously the option, and the infamous also try an exception or an A. So what it changes here is that it's just a type alias. So we see that all this happens at the type level. There's no structure here, no wrapping, no sum, piece class. All this happens at the type level. So it's effectively a zero-cost abstraction. And for the option encoding, I've taken the var A as it is, and then the none, I've taken one from option, from the Scala option, but it could be anything. Maybe unit is more appropriate. Again, this is simply aliases, so it compiles without an issue. And let's see if we can make use of this, because as you see, everything boils down to the same structure, same concept. It's just you can't forget the left-hand side, and yeah, it makes sense. We have A or B, A or E, and the important thing is that we can keep expanding. So it could be A or B or C, and that's something that makes sense in logic, that works for logical propositions, for implications. And for a beginner, probably it's quite something natural, I would expect. And we don't have to define different names for what's effectively the same thing. It's basically, option is simply an either where the right-hand side, well, one of the branches is none, because that's very important, as we saw here. Yeah, we did say commutativity, so compile it again. We see that string of Boolean is equal to Boolean or string, so it doesn't matter where you put it. So we don't have to go through these conventions, right is right, left is, everything is type-driven. So, yeah, this sounds good. Zero-cost abstractions, very flexible type-level reasoning. Let's start how we can use it practically. So we'll go to a simple dummy square root function where we return an option. This is the Scala two-way, so I'm going to use option. When you see option, that's the Dotty my encoding. Well, the encoding with union types. When you see Scala.option, that's the Scala 2 reified option that has a sum. That's the option we use. So I'm having both. I hope it's not it's confusing, but well, you can ask if you. So this function simply you see we wrap if it's smaller than. I mean, if it's in the domain of the function, so we return a sum with a square root. Otherwise, we return none because there's no square root for negative numbers. So we constrain the codomain. That's nothing to see here. Now, if we go to move to Dotty, the encoding again is A or none type. And if you, for the eagle eye, you'll see immediately that the only difference is that the math square root, it's basically it's vanilla. It's a direct value. There's no wrapping into sum. The none again is the same object as you would have in Scala 2, but the square root is just a double. And so let's see side by side. You see sum in the square root Scala, square root Dotty. And yeah, well, let's keep going. Just some examples of executing this. You see, interesting, in the Scala, when we print it, when we evaluate the expression, the application of this function, we get sum 9. For the Dotty, we get 9 because as we see, there's no box in there. It's just a value, the normal double. It's just at the type level, the compiler knows that it's an optional value. It could be a none if you try the negative, as you see below. And the values below are the same, are exactly the same. So it could be exactly the same value at the runtime. But on the top, one is a case class, which is sum, and the other is just a double. So yeah, this sounds pretty good. Zero-cost abstraction, reasoning at type level. See, we can spot the problem. So let's create a format, simply format the double to string, and how do we yeah, how do we format if we go below, how do we apply format to the A0? If we look at the error, so correctly, even though the println is showing us that the value at the runtime it's a double, and println takes anything, so we'll print it. But the compiler tells us rightly that you cannot apply format to that double. That it works with println, but format doesn't work because, yeah, it's expecting a double, format expects a double, and you have an optional double, which is double or none. So that's expected. So that's an issue. How do we make this practical? Sorry. So we can, yeah, this was the slide. So I'm importing a small library. Well, it's not a library. You'll see it's just a function of 4 lines that uses the standard Haskell symbol for function application. So this tries to be simply a function application that applies to a value that's an optional. If we run this, now we get the S correctly identified as an optional string. But if you see the evaluated printed on the right, you see that it's still a pure string. There's no wrapping on that line. So yes, how do we see that? Yeah. So obviously, you might be guessing there's some kind of reflection happening behind the scenes. What the dollar application does is, if the value is one expected value, it will apply it. If not, it doesn't apply it. And from now on, I'll try to defend this way of applying a function in this unorthodox way. The AOP, I'm not using AOP, don't worry, this is just a generational joke for us guys that have been doing JVM since the start, and probably we are scared about the AOP. So there's no AOP, but obviously there is some kind of trickery happening. But I'll show you, it's very lightweight trickery. It's simply, let's see this. And it's simply a test. A test if the x is an a, then applies the function. If not, it's an e, but for familiarity, I don't think e has an error. It could be any e. It could be even a set of unions, or it could be nothing. If you're applying something that is not a union type, you apply something directly, it will work. If not, and the other long line is simply some type level constraint and hackery, just to make it make it sound, so you cannot apply to anything. Even though there is some kind of optionality, it will only be applied to the values that make sense for that application. So let's see the example. So when I'm doing this, we go directly. So it returns the string. If we apply a negative number, we get the, what is it? We are formatting number, sorry, it's not, see, it's not doing the square root. If we were doing the square root negative, then the negative should return a none. Yeah, so we're getting the none. And if we pass, sorry, the A0 is just a normal application, it's not using this. The problem is you couldn't apply the format. So, but let's see the format to something that is not, it shouldn't be applied. If we go to we pass a string, for example, so correctly the compiler complains, don't pass me a string, pass me something that has a chance of succeeding. That introduces some kind of basically soundness or sanity to the system, but keeping it open for basically a world where values could be different branches. Moving on, you're telling me, okay, Lander, you're applying an option, you're basically doing map without map, simply by applying the function directly at the value level. But what happens if I want to apply the square root twice? So obviously without the dollar, without basically my helper function, this will never work. But let's try to do the, so yeah, this never worked. And let's see how we do it with Scala 2. With Scala 2, we create an option, and then we flat map twice, and that's how do we apply it. Obviously, we'll use it for comprehension, we'll use a nicer syntax, but basically we're applying twice, so we see how we return 3. We are passing 81, so the square root twice, that will be 3. In Dotty, we see that it also returns 3. So what is this? I'm applying the same, I'm using exactly the same functional application that I did for the format. So how is map and flat map the same? What kind of sorcery is this? Yeah, I know I put a very psychedelical first slide, title, then it's 4 o'clock, 2 days, no coffee, no breaks. But believe your eyes, that's really truly happening. And I'll explain why. I won't bring the mob meme again. Let's explain it, why this is happening. So we have again, well, there are a few things here. In line 11, we have the normal application of a square root, returns an optional double, correct? If we go to 12, we apply it with the dollar thing, and in line 9, we apply it twice. But sometimes the compiler is not good with the aliases, so let's basically desugar the alias to double. So with the alias, now this rule should work. Type. So it's now Dotty is correctly inferring, not only getting the value, but correctly inferring that this is an option of type. So even though I apply a square root twice, which requires a flat map when you have a value level option, this is happening. And sorry, I'll desugar the one below as well. So yeah, shouldn't this be option of double? So basically, this is what we would expect if we apply it twice. This is an option of double. Apply it again to value A0. So it should be an option of double. So yeah, you're right. The same, both things are true. That's an option of double, an option of double. Why? Let's help the compiler. This is correct, actually. The compiler is complaining just because I'm using aliases. If with the sugar a bit, the compiler will start seeing the light. We say we peel down one of the layers of the option. So now we have option of double or none. Let's see. The compiler now takes it. It's an option of double. And why is this happening? Let's peel this down again. And now the mystery starts becoming clear. Because double or none, the or none is simply equals none. By the rules of logic. So is that correct? Is there any basically unsoundness happening? Let's say, yeah, this probably is only a double. No, the compiler is basically doing the right thing. That's not a double, but it could be. At this point, yes, it's a double. If we print it, basically, if we print this will print something. So it's evaluated to 3. But because just we are in the realms of any, if we are in the realms of type thing, if we say that that's a double, we will say that's not a double. Even though the value on the line 12 tells us that's a double at runtime, but the compiler is telling us correctly that's not a double because it's an option of double. And if we now make it negative, I can see the. So now the value is none. Everything works and the flat mapping works even though we are not flat mapping, we are simply applying functions. So this is quite cool, I think. And don't believe me. let's believe the compiler. Let's ask the compiler what they want. Yeah, I forgot to say that I use summon. I mean, summoning is we try the compiler to basically spawn a proof of this statement. So I'm saying option is optional double. Let's see what the compiler tells us. Yeah, it's correct. It's proving that it's happening. And you imagine this is go forever. Yes. It's just a stack of monads that collapses into single monad because everything happens on the type level. So, is there a monad? I don't know, but this is one of the examples that probably you don't need to introduce monads to for a beginner. It's just a double or a none, or whatever unit or not negative number or whatever. Maybe use an error instead of a none. And using option, but obviously this expands to any kind of disjunction you want to use. So yeah, I think this is very cool in Dotty, and yeah, kudos to EPFL and Lightbend for this work in the type and the basically type system for Dotty. Trying to justify this unorthodox way of applying functions. Let's think about. So, do you know when we started? So, this is normal function application from A, B, or C. So, we get an A to C. That's, well, we all know. So, what happens when we introduce optionality? So, now we have an F from A to B or C. And that basically flows into two branches. After the first application, we go to the, could be a B, in which case, in this logic, in this flow, we are applying one function we have, which is from B to D. So we end up having a D on the top branch. But in the lower branch, if it's a C, we don't have a G, for example, cannot apply to C because specs are B in the domain. So, where I'm trying to go with this point is that we should maybe strive for a more rich, more powerful composition of functions that includes this optionality, this branching of logic. We could be in this scenario, or we could be that other scenario. Obviously, this at the moment happens with boilerplate. We'll use basically case statements, pattern matching, and if. Basically unprincipled control flow. If we follow these types, and we have these two functions, and we have these type signatures, there's only a single way of applying these functions that will make sense. So it's a completely determined flow of a program by the types. And we don't need to do anything. We could even linearize and apply the two functions, and in which case it won't apply G, in the other case it applies G, depending on the branch is correct. And I think this is going to become more important because the types are getting more specific. We have dependent types, we have refined types. So if the types are so specific, they don't only constrain the values for the possible set of values for a value, but they also constrain the possible flow of the values in a program. And I think it's a waste not to use that information, not to the compiler, not to make use of that to basically allow principled, type-safe, type-driven application of functions, basically compose into a bigger function without having to do our branching ourselves with ifs, with case, basically the pattern cases. I really believe that really truly can change how we do FP, how we apply functions. So again, just an example, a bit more, not complex, but a concrete example. We have something that, again, square root, but from an input. So a logical flow diagram from a string to, if we apply to int, that will be a try. an int throwable, well, probably better validated with some other significant error, but anyway, let's go with a try. With the try, if on the branch, if it's an int, it will go down, and you can apply the sign, which is, the square root. The square root function, I changed it. Instead of, it's now more, I think it's a better function because instead of constraining option of double, the code domain constrains the domain. So now only takes a positive value. If it is a positive value, it returns a double. So there's no optionality because now the optionality is on the, the optionality is because the type is more specific. So this will be a pain if you don't have this application because then you need to do checks, and that's why we go to the code domain, the result. When, as we know, the earlier you treat anything, it's going to be, the consequences are going to be fewer than if you do it later. So by this application, that the application only happens if the type is the type that you're expecting. Basically, you allow functions that are more targeted, that you constrain the domain, and basically have less values, less possible implementation, easier to test, and easier to reason about it. So this simply, and this could be linearized as a toInt, sign, square root. But we see that in each case there is a branch that flows into, and in the end we have basically this program, the small program, this function could return into any of these three cases. So this is a good starting point. How do you think about your function? So if we implement that in a dummy way, so basically we have nothing too much to see here. A string to int from a string to a try-int. We simply tries the toInt and wraps it in the throwable. A sign will return an either of negative or positive, and either being, again, it's simply a type alias from A to B. And yeah, negative, positive. In Dotty, there are opaque classes, probably will be a better use of this. But anyway, and then finally a square root, which now is simply from positive to double. So there's no optionality in this function. If you give me a positive, I'll give you a double. So it's much easier to reason about. But again, the problem is how do we apply it? So let's have this input to the string -81. We first apply toInt, that's fine. Nothing to see here, no function application. Now, how do you sign to the try no int? Well, again, you need map, you need, in our case, there's no map, it's simply an A throwable. Again, it's just a unboxed zero cost abstraction value. So we need to use this, again, the dollar for application. And so we see the flow here. First is a try to int, then a try, either negative or positive. Once you apply the sign, once you apply the sign there to the try, you'll get try of either negative, positive. And finally, you get the square root, which is apply the square root to sign. And that's an try, either negative, and now the positive has swapped to be a double, shifted to double because square root knows how to do positive to double. So all this flow is simply without no logic here, no map. You don't need to think it's a map, a flat map, mono transformers. I mean, already here we would have hit with a big wall of needed library support, needed abstraction, needed cost and performance, and with a very steep learning curve for beginners. Whereas if you go to the previous diagram, this is quite a simple logic. Double, negative, throwable. So can we again, the error is the compiler is getting confused by this construction, but it is correct. I'll show you. If we simply remove the type inference, it will work and returns a negative 91 because, yeah, when we signed it, it was a try either negative a positive, that was a negative, and then a square root only takes the positive branch. So basically we end up, finally we end up with a negative. If we change the input to something that happens, yeah. A minute, okay. We get a 9. And if we make something that is an invalid value, so we'll get the number from the exception. So I have 1 minute, so let's, yeah, I think that's basically what I wanted to show. It's what happens, sorry, give me a minute. So this whole thing boils down to the sorry. If we try to prove it, what I was trying to prove is that this is equal to simply a negative, double, which is the expected result, a negative branch, or a throwable. Here. And sorry, 1 minute and finishing. Let's make this statement. Sorry, yeah, it's a bit difficult to. Yeah, it's a bit difficult to see if I. But I mean, the type. When I put this with the fact, and basically the lesson here is not only that the type on the top. Requires a lot of abstraction, requires a lot of scaffolding, it's difficult to understand, requires mono transformer, blah blah blah. It's that you could, from that logical graph of what's the logic of your program, it wasn't difficult. You cannot make the connection from this to this. If I see this, it will find difficult to understand that this is really what.
Does try take 2 type parameters?
Huh? Yeah, maybe I'll try. Sorry, 2 type parameters? Yeah, I think you're right. And sorry, is it? Yes, either. Yeah. Sorry, but the thing is, I was trying to maybe so there is a. If I go to the more complex one. Sorry. The thing is that it's difficult to make the connection to this. If you see the flow, you see that those are the possible values. And if you try, the compiler will tell you that's exactly the same as that. Yeah, so sorry for that glitch, but it was a bit fast-paced. Thank you very much.